Thank you so much, and thank you all for joining us today. I know that there's a busy slate of ocean sciences meetings coming up this afternoon and right afterwards, so we'll probably try to keep this brief. And so the purpose of today was just to kind of recap our progress and activities that we've done in the working group over the last year. And so our working group is on basically air-sea interaction on the mesoscale and frontal-scale globally over the ocean. So we have, these are our members, just to recap of all our members of our working group. And so the objectives basically that we put into our prospectus were to formulate and coordinate observational and modeling efforts to quantify the oceanic mesoscale and its impact on Earth's climate and hydrological cycle and other components of the Earth climate system. And one of our main activities that we've now completed was to produce a review paper that synthesized our current understanding and gave a kind of an overview of the current open questions that can help inform observational campaigns and model development, basically focused on air-sea coupling in the Earth's climate system, and they're basically integrated impacts. And these integrated impacts include the impacts on large-scale atmospheric circulation, Earth's hydrological cycle, specifically the distribution of precipitation and terrestrial droughts and things like that. And then feedbacks onto the ocean, including ocean dynamics, biogeochemical impacts, among many others that we learned about as we were doing the review paper. The second key thing that we want to do with the working group was kind of develop diagnostic frameworks that we can use to basically analyze models and use observations to do that using a robust set of metrics. And so a number of investigators have proposed various ways of evaluating some broad measure of air-sea coupling and the strength of the coupling in model and observational frameworks. And so we wanted to kind of bring those all together and evaluate them, compare them, and propose essentially a standard set of metrics that we can use to make progress on using observations to improve model simulations of the Earth's climate. And finally, we wanted to kind of identify consensus on uncertainties in air-sea coupling and directions forward for both observations and modeling. And right now, there's obviously a number of different satellite platforms and in-situ observational campaigns that have either been proposed or are set to go into operation. And we're hoping that our working group can kind of guide these efforts to talk about optimum sampling strategies or what kind of variables and things that we need to use to to achieve our objectives. And we want to also use this time to kind of motivate coordinated process-oriented modeling and observational studies, maybe not necessarily within the framework of the CLIVAR working group, but propose this to the community and to the funding agencies as good directions to go that are based on our best assessment of previous work. And finally, we wanted to kind of broker community efforts with US CLIVAR workshops and other efforts to go forward in advancing the science here. So basically, our working group addresses many aspects of CLIVAR research challenges. So I just stole this off the US CLIVAR website. So the mesoscale air-sea coupling and kind of the composition of our working group and also the content within our review paper touched on basically all these different science and research challenges. So seasonal to subseasonal prediction, decadal variability and predictability, climate change, the extreme weather events, the changing polar climate, ocean carbon and biogeochemistry, and then coastal climate. And there are a couple other ones that were not on this list that I think we also are able to contribute to. And this is the Earth's hydrologic cycle. That's specifically distribution of precipitation and drought, things like that. marine heat waves, both the coastal and open ocean expressions of marine heat waves, and finally, ocean ecology. So the links between the ocean biogeochemistry, the ocean physical state, and things like species proliferation and distribution, etc. So our recent activities this year, of course, we were impacted with COVID like everyone else, but we actually were able to do quite a bit this year. And the big task that we did was wrote this review paper and submitted it to the Journal of Climate in December, so we should probably be getting reviews back pretty soon. And that was actually quite a really nice experience to get everyone's feedback and just learn all the different nuances and work that has been done in the last 10 years. And this follows on review papers that were done as part of CLIVAR activities. This Justin Small's 2008 paper on this topic, and then also a few other ones that followed that on the Gulf Stream and Kuroshio and things like that. So this paper kind of provides a synthesis on where we've, on the advancements of the science. And it went in a little bit different direction than those previous review papers, in that we focus more on the impacts of coupling on climate scale systems, and which I'll talk about shortly. We've actually had a very nice group of seminars every roughly 1 to 2 months with two of the working group, from either members of the working group or community members that are working on something that is very related to our activities. And right now we're in several of us on the working group are assisting in planning the US CLIVAR Gulf Stream workshop that will be held at Hui in June. So this is just a list of kind of our bi-monthly seminars, science seminars, and they touched on a number of things, including the emerging role of ocean currents on air-sea coupling and the larger scale impacts on Earth's climate, and also on evaluating the role of air-sea coupling in climate scale projections into the 21st century, and then also on more detailed topics related to metrics of air-sea coupling and the role of timescales, spatial scales, and also on looking at the evolution of our array of surface flux measurements and the evolution of bulk flux algorithms and things like that. So this has been a really nice really nice kind of thing that's really informed our discussions going forward. So our review paper that we've submitted, it was titled Ocean Mesoscale and Frontal-scale Ocean Atmosphere Interactions and Influence on Large-Scale Climate. And we reviewed many aspects of the role of the mesoscale air-sea coupling on the climate. And we're more focused on processes that were forced on oceanic spatial scales of about 10 to 1,000 kilometers. So this touches on kind of the upper limits of what we call submesoscale now, through the mesoscale and to what we would consider kind of the larger scale. And so this is really a frontier of both the modeling capabilities and observational capabilities, and as it tests the limits of spatial resolution and temporal sampling in resolving these processes. So instead of kind of going through the whole review paper, I just wanted to just provide a kind of a list of some of the lessons that we've learned and some of the key points that we made in the paper. So basically, we outlined the impacts of the air-sea coupling and how it touches many key aspects of our climate system, and including the hydrological cycle, ocean biogeochemical cycles, and climate change. And so we really wanted to make a strong case that this coupling was an important part, an important research area, and it had very definitive applications, societal applications, and applications for our knowledge of climate change and a number of different aspects of the Earth's climate system. We also outlined the importance of sustained global observations of the oceanic mesoscale for both in situ and remote sensing. So this would include the continued measurements, having these long-term uninterrupted measurements of key variables and the production of climate data records from them. And we also outline that a lack of measurements hampers our ability to improve weather and climate model predictions. The key aspect, obviously the coupling is forced at the surface and is completely contained, or a key process in that coupling is the heat, momentum, and gas flux observations at the surface. And so continued improvements and collection of these flux measurements are really key. And the emerging evidence is now indicating that surface current measurements are a critical piece of our current flux observing system. And so one of the things that we really want to get, a point we want to get across is that, we need these surface current measurements on a global scale over most of the ocean. And this will help us improve our, our representation of these and our understanding of the system. And the oceanic submesoscale is now being recognized as important for air-sea coupling and the large-scale climate. So some of the processes that we think that we're observing on the mesoscale, it turns out there's a lot of submesoscale details that are embedded in that. And so, we need to, be able to observe it at higher spatial resolutions. And of course, this sets timescales of processes that we need to observe. So this is really kind of a frontier that we need to understand the mesoscale coupling as well in here. And there's just a lack of measurements and modeling studies due to challenges that are specific to submesoscale. So some of those challenges include model parameterizations, resolution capabilities, and temporal sampling. And finally, there's a real critical need for these diagnostic metrics for comparing air-sea coupling between models and observations. And this is a crucial thing that's needed to improve climate models and understanding key physical processes of air-sea coupling. So those are some of the key points in the paper that we made, and hopefully when it comes out, you can read more details and about that. Our working group is memberships are pretty active, or really active, in a number of these different areas. So activities in the previous year that we've been involved in include the SMODE, the submesoscale ocean dynamics experiments that we started a couple years ago and just completed the pilot experiment. And we've been involved in CLIVAR sponsored workshops on the Gulf Stream Weather and Climate Workshop, and also the Tropical Pacific Observing Needs workshop that was last May. We have some working group members that are involved in these climate model production and evaluation, including the high-res MIP2 and Primavera, and a couple of observational type campaigns, including OASIS, Diamond, the WACM Winds and Surface Currents Satellite Concept, Butterfly. And some of our members are also involved in the DOA Department of Energy wind projects in coastal areas. There's an international effort, Hotspot 2, and also the Casper Extension project. And so there are probably some others too, but these are kind of the ones that we could think of. So the future activities, so we'll have a community workshop that we plan in spring 2023, and we were hoping to do it this year, but obviously that's not going to work. So so if you're interested, please let myself or Hyodae know so that we can include you in the invitation list. We're going to continue our bi-monthly webinars. So we've got a few more speakers planned. So we're going to keep that going. And then we're going to ramp up efforts on data repository and evaluation of diagnostic metrics so that we can address our second goal of the working group, and to kind of assess impacts of air-sea coupling and observations and models. And we're hoping that maybe what comes out of that is either a paper into itself or maybe a white paper that can give kind of a best practice for ways of evaluating air-sea coupling and observations and models. And we're also going to focus some of our science discussions and future work on the impact of surface currents on air-sea fluxes and climate. Excuse me. Air-sea coupling is a source of predictability for mid-latitude weather and climate, and links to marine heat waves. And we anticipate that these activities will feed into either further review papers or into another white paper, depending on the timing of our activities. And we're going to continue involvement in current community activities such as satellite concept missions, for instance, Wacom or Butterfly, and workshops here. So, and finally, so those are kind of our main activities. And I wanted to just give a couple, 2 or 3 brief kind of summaries of recent papers that really highlights why the direction of our working group and why we think some activities are important to focus on during our last year. This first one was a nice paper, recent paper by Sakura Ben-Kerman and Lucas Lorindo, and they basically looked at the impact of the Kuroshio extension on precipitation in the Pacific Ocean and downstream into North America. And what they did was they looked at, there are years when there's a lot of eddy activity in the Kuroshio, and there are years when there's not. And so they just took a look at the precipitation differences between in January, February, March, between active eddy years and inactive eddy years, and to see, how that, how the precipitation responded to those events. So the top one just shows observations from the TRIM precipitation analysis between active and inactive eddy years. And it shows basically that there's a big difference all across the Pacific. In some places, there's more precipitation. So over the much of the US West Coast and the Eastern North Pacific has more precipitation during active eddy years. And then there's big swaths within the Pacific where there's less precipitation. And of course, for this sort of precipitation increase that's impacting Southwest US or the US West Coast is actually quite intriguing, because it suggests that there's possibly some sort of, that there's a link between the ocean representation of ocean eddies within observations and models and the precipitation over the US West. And so it has implications for drought and water supply management and seasonal and subseasonal predictability. They also took a look at high spatial resolution simulations and low spatial resolution simulations. And essentially they found that if you increase the spatial resolution of both the ocean and atmosphere, you get a better simulation of precipitation variability between eddy active and inactive years, especially over the US West. And in the low resolution simulation, you get something that looks completely different from the observations. And so basically the key point here is the accurate representation of air-sea coupling and the resolution of eddies in places like western boundary currents will improve seasonal, subseasonal, seasonal predictions in North American precipitation. Another recent paper that is pretty exciting shows basically that if you include surface currents or the relative wind effect in an atmosphere-only model or in a coupled model simulation, that it has actually quite a strong impact on the storm track in mid-latitudes. And so this was by Hyodae Seo and co-authors. And it looked at basically a sensitivity analysis where you included ocean currents in the surface stress. So you either include them or you don't include them. And then you look at the evolution of the 500 millibar height field in the atmosphere. And essentially, the main point was this, is that including ocean currents leads to stronger ridges and troughs downstream. So this study was conducted in the Southern Ocean. So this is Africa here. And then this is kind of the Southern Hemisphere storm track down here. And so, including the ocean currents specifically in some of the strongest places, so along the Agulhas currents along Africa, and the Agulhas retroflexion and the Agulhas return current here, that including those in the stress formulation basically changed the storm track behavior quite a bit. And so it led to stronger ridges and troughs downstream. And so this basically says that including those surface currents in atmospheric simulations has a big impact on our predictions of weather and climate. And the last thing I want to share is that I'm actually part of the S-mode field experiments, and one of the elements of that, so there's several different goals, but one of them that's relevant for this working group is to look at the atmospheric boundary layer response to sub-mesoscale sea surface temperature and surface current variability. And so I participated in the pilot field experiment in October of this previous year on the Oceanus. And we went out and basically launched a whole lot of radiosonde balloons in such a way that to try to resolve coupling within the, to resolve this sub-mesoscale coupling. And so we're still analyzing the data, but there's some promising responses of the boundary layer winds to some of the currents and SST structures that we're still trying to understand. But this is a fairly, this observational campaign was designed specifically to try to resolve these processes. And there have been few studies that have really tried to do this. And one of the things that it takes is launching a lot of radiosondes. So we launched 90 over a 5-day period. You know, within the next IOP for this October and the following year, we're hoping to actually be able to launch more than that to try to you know, to try to kind of get observational evidence of what kind of processes are at play on the sub-mesoscale coupling. So anyway, that's all I have. So thank you very much, and I'll take any questions.
Thank you, Larry. So if you have any questions, you can use the raise your hand button, or you can type your question into the chat box. There was a question earlier today by Gudrun. Is there a translation of acronyms somewhere? So we will have a test on day 3 of the summit for the acronyms. But I do know Hyodae did respond that he'll spell out the acronyms in the slides, and we can share that with the panels. I also know that in the TPON workshop report, there is an appendix that has a list of acronyms. So hopefully we'll capture all of them, if not most.
Yeah, sorry about that.
So any questions for the two? Yeah, Shane?
Hi, Larry. Hi, Hyodae. Thank you very much for the presentation. So I think I remember in one of your slides, you said that, you know, there was a need or there's a recommendation to have global, remote, and in situ observations of surface currents. So how does the working group think we achieve that from the in situ point of view?
Katie, do you have an answer?
So so it has to be done through remote sensing, so the spatial coverage that obviously, but you need to know this. I mean, it's definition of surface current, right? We had a workshop back in 2020, long time ago. How we define surface currents, right? So we need this in situ measurement to look at this vertical structure of the surface current, different, I don't know, conditions to be able to tell, and they can hopefully they can be used to calibrate the remote sensing of surface current. The point here is that surface current has to be measured at the spatial scale of surface winds, because we know that there's a very strong scale-to-scale coupling. So if you think about mesoscale winds, so oceanic mesoscale winds, the importance for driving ocean mesoscale variability and ocean dynamics, that the whole point of this working group, we need to be able to measure surface current at a similar spatial and time scale, which is even more challenging, right? You can do something like existing altimeter data or SWOT measurements and other cellular measurement and give you a little bit more detailed structure of the surface current, especially the ocean boundary current regions and things like that. Those are the important areas where the momentum flux and heat flux can be very, very dependent on how you represent surface currents. And I think this is the very beginning of this or research coming out, burgeoning research about how the surface current impact the air fluxes. And we really don't, there's a lot of interesting dynamics, impact on the ocean and a little bit of atmosphere, but we don't really know the large scale consequence of those momentum coupling through the air-sea vertical momentum shear. And I think, yeah, rambling, but.
Thanks. Antonietta, I see your hand raised.
Yes. Thank you. Thank you very much. Thank you. This was a wonderful presentation and very, very interesting. I just have two questions. One concerns the, I think from your presentation, it seemed that there has been a lot of, this working group is really focused on trying to understand the effect of the small scales on the large scale. So you go from small scales in the ocean, how that can affect the climate. I think it would be also interesting to go in the opposite direction. So you have mentioned the influence of the ocean features on atmospheric boundary layer winds. So especially I think in the context of, for example, offshore wind energy or, for improving weather models, I think would be important to identify climate regimes that can affect the ocean surface and affect also the shorter term predictions. So that's one thing. And then the other one, I was just curious how you are going to apply what you're learning in this working group to maybe better understanding of marine heat waves, of ocean extremes. So which aspects are you going to look at?
Yeah, that's a good question. So in the review paper, we did look quite a bit about the, there's been a lot of research, obviously, over the last several decades about the, how you get basically SST anomalies in the mid-latitudes, what kind of weather forcing, if you apply white noise weather forcing, you get just this rich scale of ocean anomalies and things like that. And so we're hoping to bridge that kind of avenue of research into also looking at the spatial structure. And what spatial scales matter. So, it is kind of getting the spatial dependence of the coupling. So on smaller scales, there's a different processes of coupling that occur over kind of the larger scales. And so part of our working group and part of the review paper was to try to, join those two avenues of, separate thought and bring them together into kind of a bigger picture idea.
And what about the marine heat waves? Did you, so which aspects are you going to, too many questions at once.
Oh yeah, sorry. So part of that is part of the SST anomalies that are predicted in these sort of models also include basically marine heat waves. And so there's a component of marine heat waves that are forced by climate change. And right now we're not focused as much on that impact as that process as much as we are about what processes form warm SST anomalies in the first place.
Yeah, I think that's a good strategy. Thank you.
Okay.
I'll take a question from Hai Long, then Patrick, and then Gudrun. So Hai Long.
Yeah, hi. Thank you for the very nice presentation. So I'm an atmospheric modeler focusing on clouds. So oftentimes we have seen persistent biases in low-level clouds and wondering how much is that due to air-sea interactions, surface fluxes, and but for model evaluation of surface fluxes, we always rely on products like OA flux or reanalysis, but we understand that those are also derived maybe from bulk with observations, but also depends on bulk schemes. For some regional biases, is there any other sources of more reliable observations, maybe more consistent, like you also have not just surface fluxes, but also wind stress and the gradient in temperature and moisture, those kind of measurements? If we want to, even just a field campaign, or just a site, a buoy site, or so where to find those reliable data sets for model evaluation?
Yeah, that's a good question. So the Jim Edson obviously has several of the in situ bulk flux or in situ flux measurements from directly measured things like that, and he does have the data there. So I would first start with him to see it, but those are obviously just at point measurements for the site. So for kind of global gridded surface flux measurements, we're still, the kind of data sets that you mentioned are still kind of the, more or less, the most widely used and what we have right now. And one goal of our working group is to try to motivate for further improvements in that. So the question is, are those surface flux data sets enough? Do we need better ones, and how do we get there? And so currently we're trying to build the case that yes, we do need better ones, and we need that for model evaluation, and specifically trying to pick out what kind of physical processes, or what kind of things in the models do we need those fluxes for. And I think the review paper does that a little bit. And I don't know if there's anything else you want to add, Hyodae.
Yeah, so I guess some marine boundary layer measurements are available from historical institute data sets, observation field campaigns. So I guess one thing we could do as a working group is to point to those existing data sets, the boundary layer, moisture clouds, and but there are not many boundary layer profiles of the ocean, but there are data sets like historical data sets and ongoing field campaign that does provide some indication of PVL structures, moisture variability, and profiles. So and those can be used for model testing, but that's of course very tough test for the model to reproduce a sort of snapshot boundary layer structure. But that does give you some indication if you have enough data set to make a statistics in the model versus statistics in the observation. I think that could be very good in the validation data sets for the model, for the sort of things like low-level clouds, which are very notorious problem. But these are, of course, very spatially inhomogeneous. So a lot of coastal data sets, some tropical oceans, but many are missing. So could have a uniquely different set of challenges to use those data sets.
But if you do have those data, for global model can use like single column or replay mode to try to get the other conditions correct, so that we can test even offline test of the algorithm. That will also be very helpful.
Yeah, so we can find any marine boundary layer, marine air-sea flux measurements, and then point to to the community whether these are the kind of latest, most quality control data set that can be used.
Great.
Thanks for the comment. That's great.
Yeah, thank you.
And I should mention too that the scatterometers measures surface momentum flux, and so an instrument like the Wave and Current Mission, or WACM, which there'll be a town hall regarding that, and the S-mode experiment too, advocating for a mission like that to give global momentum flux measurements, including surface currents, I think will be a really step forward in that direction.
All right, and I just want to double check. Can we take the last two questions, Larry and Hyodae? You guys okay in timing? Okay. Patrick, go ahead.
Awesome. Thank you guys for the presentation. I had you mentioned at the beginning, Larry, for the about how your work corresponds to the polar climate focus area, and I know it does, but I'm gonna ask this way. I was curious, what kind of work, like in the review paper, do you guys cover the link between these air-sea fluxes and the polar climate? And what are your kind of plans going forward? Are you guys thinking about having any more focus on the polar climate and the air-sea fluxes there? And then related to that, I was curious if that diagnostics package is considering the polar climate areas, and particularly how these air-sea fluxes, can that package handle sea ice in the grid box, for instance, as a question. And part of my motivation for this is I'm trying to find a spot, maybe within US CLIVAR going forward, about where a future working group or even workshop would fit in terms of high latitude air-sea fluxes in the air-sea ice ocean transition layer, because in some of my work and other work is air-sea fluxes and how they're represented in climate models, particularly in the Barents-Kara Sea region, goes a long way to tell you the pathway of how much the Arctic is going to warm over the next 50 years or so. So that's kind of my background behind that. So anything you can provide would be helpful.
Oh, that's that's actually fantastic. And what I would say is that for as far as our working group kind of goes into that area, to high latitudes air-sea interactions, is that it's mainly the link of the storm track with the ocean in that area. So we don't we haven't really looked at sea ice specifically, or regions directly into the Arctic Ocean, but we do look at the impacts of air sea coupling on the storm track, which feeds back onto the air sea fluxes in those regions. So so we don't specifically look, I think, at kind of what you're proposing to do, even though what we do does have some implications for it. And I'll just say I am working on a project in the Bering Sea on looking at air sea fluxes in the sea ice and how it's feeding back onto the atmospheric circulation. And so it would be an excellent topic for a working group on its own that focused more specifically on that. And so some of the work that this working group does could inform maybe progress in that area too.
So I can add really quick. I looked through our draft again. We don't have any mention about Arctic or sea ice covered oceans. So I will make sure we mention some of the aspect in that revision of the paper, because at the boundary layer coupling physics is very analogous over sea ice compared to, say, open ocean western boundary current, because sea ice act as a kind of very strong diabatic contrast, forcing contrast force that affect the boundary layer structures. And even more persistent compared to ocean system temperature front. So it can be a much more dramatic impact on the boundary layer stability and kinematic profiles. So there are some papers that look at this kind of similar mesoscale air coupling applied to Arctic and look at the similar boundary layer coupling dynamics, but there are not many. So I guess I think this is an area where I think community can maybe focus more into, because ice is much better resolved, and Arctic Ocean is warming. They are much more diabatic forcing coming out of the ocean. I guess this is an area where we should be looking at more detail. So I make sure to make some comments on the paper about that. So thanks for the reminder.
Yeah. And then one other thing, I think now is a good time with the mosaic observations. We have, 1 year of the surface flux measurements from the towers that they put up around mosaic. So getting at these fluxes over sea ice and in the Arctic seems like a good time, because we have a data set, unprecedented data set.
That's fantastic. Thanks.
All right, I think we'll end with a question from Gudrun. Go ahead.
It was great to hear that question, Patrick, and that you're going to address this. The Arctic is such a critical region, and where surface fluxes are really important. I take it WACCM is a scatterometer, is that correct?
Yes, that's correct.
Okay, my question is actually about, you showed a slide from Ben Kurtman's group about these during years that there's a lot of eddy activity in the Kuroshibo. That's when you get precipitation in the US Southwest. I had seen that a couple of years ago at the last AMS meeting that was in person, but I heard him give a talk on it. So my question is more on the oceanic part of that. So when there is a lot of eddy activity in the ocean there, does that last throughout the season? Is there a lot of interannual variability? So 1 year it's a lot of activity. What is that variability like?
Yeah, that's a good question. So it is, there is interannual variability, and there's a lot of interannual variability in it in the eddy state of the Kuroshio. So there are years that there's like a large meander states and other things like that. It does vary year to year, and I'm not super familiar with what drives that, other than variations in the flow of the Kuroshio in the western boundary current there. So
and it tends to last throughout the winter season when it's active.
Yeah, that's right. Yeah.
So they are persistent. Eddies persistent lifetime scale of like 16 weeks or longer. So they have very long persistent time scale in terms of S2S prediction time scale. And then Kuroshio has this decadal variability that has a stable eddy condition versus unstable eddy conditions. So I think it does vary interannually, but also very strongly in decadal time scale. So what Ben Kurtman
Approximately what time scale?
Decadal, so it's like maybe 5 to 10 year time scale. There are years of a stable Kuroshio front and then years of unstable Kuroshio front. Antoniera knows very well about that kind of Kuroshio decadal variability, and then eddies reflect that stability of the Kuroshio front. And what Ben Kurtman did is initialize the model with that particular stable, unstable condition, and look for sub-seasonal to seasonal timescale downstream rainfall response, and find that very strong response. And that's because eddies are more persistent throughout the whole winter, given that decadal state of eddy.
Yeah.
So that's very interesting work.
Okay, thank you.
All right, I think that'll wrap up our webinar today. So thank you, Hyodae and Larry,